not all things collide head on. Mostly they don't. And so we do need to be able to apply what we've been doing with collisions, namely apply the momentum principle, apply the energy principle, try to predict what's going to happen. We have to be able to apply that in 2 or 3 dimensions, not just one. So an example that's discussed at the end of the chapter is actually the famous Rutherford experiment, where Ernest Rutherford and his colleagues at Cambridge actually figured out that the nuclei of atoms were small and massive instead of sort of large and spread out and low mass gooey stuff through a collision experiment. They were colliding alpha particles, which you've heard of. Those are just the nucleus of a helium atom, 2 protons, 2 neutrons. And they're emitted by radioactive decay from various sources, so they're usually some around. With gold nucleus, he shot these at gold foil and looked at what happened. And so basically he had a little alpha particle coming in, but gold foil, he used gold foil because gold is very malleable, very low Young's modulus, so it's very easy to make a film of gold foil that's extremely thin, very few atoms deep, just by pounding on it and spreading it out. So you can make an extremely thin foil, and that makes it probable that an alpha particle coming in and going through the foil is likely to interact with only one gold nucleus, not with lots of others. Remember that the dimensions of a nucleus are around 1 times 10 to the 15th meters, but the cloud around the atom, the interatomic bonds, are on the order of 1 times 10 to minus 10th meters. So we have a 10 to the 5th difference in the size of the nucleus, the size of the atoms, or the length of the bond. And therefore, any particle that gets close enough to this gold nucleus to interact with it is not interacting. The interactions with the next one down or the next one up are really negligible. So we have these alpha particles coming in, and it's not necessarily going to hit a gold nucleus head on. So we'll call this one. And gold is massive. It's got, what? It has 79 protons and roughly the same number of neutrons, so its atomic mass is actually 197. 80 and 80 is, yeah, so lots of neutrons. But a nucleus is charged. Now, what about the electrons? They really aren't playing much of a role in this at all. This alpha particle is coming in fast enough, it's just kind of zipping right through the electrons, not interacting. And they're very low mass, but the big interaction is with this nucleus. So it comes in, and is there going to be, even if it misses it, is there going to be an interaction? It'll keep going. But it'll be what? There is a gravitational interaction. There certainly is. The mass of an alpha particle is small, and the mass of a gold nucleus is. There's going to be a big electric interaction, though, isn't it? Because this thing, since it has 79 protons, it's got a charge of plus 79 times the charge of a proton, and this has a charge of plus 2e. It's got 2 protons and 2 neutrons. So definitely an electric interaction. And they don't need to touch to interact electrically. So if it comes in like this, though, is it going to be attracted or repelled? It's repelled because both positive, right? Like charges are going to repel. So it's probably going to come out with some momentum that way. And so we'll call this P alpha initial. We'll call that one P alpha final. And we're applying the momentum principle here. What has to be the direction of the momentum of the gold nucleus after this interaction? Well, okay, so what's the initial momentum of the system? So this is, here's our initial state. What's the initial momentum? That way, right? So P initial is going that way. And what has to be true, if we're taking both things as a system, what has to be true after this interaction? It's got to add up to that, doesn't it? But it looks like we've got a positive y component here when we didn't start out with one, right? What does that say about the gold nucleus? It better go down, hadn't it? Because the gold nucleus because the sum of these two things had better add up to that. Okay, are we happy with that? So we have here's P initial, and so if we have P alpha final, we need to add something to that that's going to give that. So if we're, here, we'll do it this way: P alpha final. Then we better have the final momentum of the gold being down, and not necessarily equal magnitudes. I mean, but the y components have to be equal, don't they? So we know kind of what's going to happen, and what actually gets measured in these experiments is the so you have how do you figure out where the alpha particle went? Well, you've got a detector up here that detects it. And so what's usually measured is the angle between the initial momentum and the final momentum. And so here it's, and so there's, and although we could just write px, the x and y components, because of how this data gets reported in the world, we usually talk about these two angles, theta and phi. So what we want to do is write the momentum equation and the energy equation for this situation and see if we can predict what's coming in. So let's say we know the mass of an alpha particle and we know its initial speed. These were 10,000 electron volts, I think. I'll look it up. But so we know this. We know the initial momentum of the alpha particle. We're going to predict what happens finally. So let's write some equations and see where we get to. Okay, so we have the initial momentum of the alpha particle has to equal the sum of the final momentum of the alpha particle and the final momentum of the gold nucleus. And we'll write this out in component form because there's both x and y components here. So this, well, so we have in the x direction, the x component is just the magnitude of this, so it's going to be, because this momentum is P alpha initial 0, 0, because it's in the plus x direction, is equal to the final momentum, the x component of the final momentum. Now remember, we can write this as the magnitude of the final momentum times a unit vector in the direction of its momentum, and we use direction cosines to get that. So the x component is going to be a cosine of this angle theta here, and the y component is going to be the cosine of that angle, so cosine 90 minus theta, and we're working in the xy plane. And likewise, we can write this one as the magnitude of the final momentum of the gold times, we have cosine of the second angle phi, and then the y component is actually the cosine of that angle, which is 90 plus phi, so we have so we can just fill this out. So we've got the magnitude of the final momentum times cosine of this first angle plus the magnitude of the momentum of the gold times the cosine of that other angle. And then we can write a y equation too. So we have the y component 0 here, and that better equal the magnitude of this momentum times the cosine of 90 minus theta, and the magnitude of that momentum times the cosine of 90 plus phi. So basically we have, so far we've got two equations here. Now how many unknown quantities do we have? What's unknown here? Theta and phi are unknown. We also don't know the magnitudes of these two momenta. So we actually have four unknowns, right? So we need this, that, so two angles. And we got two equations, so that's not quite enough. We can write an energy equation, though. That should help. This collision is elastic, although it wouldn't have to be, because it might be. Remember, nuclei have internal energy levels too, and if this alpha particle came in with enough energy, it might actually just transfer it to the nucleus and excite some of the protons into orbits farther away from the center. That doesn't happen in the Rutherford lucked out. He would have been so mystified if that had happened, but he lucked out because the alpha particles he had just didn't have enough energy to do that. These energy levels are pretty widely spaced. We're talking about millions of electron volts, so fortunately that didn't happen. So it's elastic, which means that the kinetic energy of the two particles afterwards should be equal to the initial kinetic energy. And so we will write that equation here. So we'll use, since we're talking about the magnitude of momentum, we might as well just use these things. So we have, this is momentum principle, and now we have the energy principle. So we have the initial momentum, magnitude of the initial momentum of the alpha particle squared over 2 times the mass of the alpha particle is equal to, these are magnitudes, and we have the magnitude of the final momentum of the gold squared over 2 times the mass of the gold. So we have 3 equations, but we got 4 unknowns. And we're stuck. we're stuck. So what would have to happen is we need another measurement. So we can't actually, we just don't have enough information to solve those equations without getting some more data. And so if somebody actually measured the angle at which the alpha particle came off, the scattering angle it's called, then you could say, okay, then I can figure out where the gold had to go. Yes? There are two ways to write this vector. But either way, they're going to be two components. So we can write it this way, or we could also write it as P alpha final x, P alpha final y, 0. And this could be P gold final x, P gold final y, 0. And then the angles really don't appear in this equation. We just have these two I mean, the angles, what this is of course this times that and that times that. But it may be clear here that we still have these four quantities we need afterwards, and so we could write this as just px plus px, py plus py. Anyway you try to rearrange it, it still turns out that we just end up with four unknowns and three equations. And so it's not a problem that we can actually solve on paper without some more information. So someone has to go make a measurement and tell us something about what happened afterwards, and then we can do it. Even if we did that, though, notice the kind of calculations we've been doing. Just tell us what, sort of, we talk about a snapshot before the collision. We talk about a snapshot afterwards. They don't tell us the path a particle moved through. Okay, all we know is just some initial final thing. So we don't know a lot of details about the interaction. How close did they get? How long were they close together? What did the path actually look like? And for that, we need to go back to our old scheme of applying the momentum principle and the position update principle again and again and again, back to this iterative calculation to find out what's really happening. Suppose we just shoot one particle at another particle and see what happens. So here's a program that starts out with an alpha particle here and a gold nucleus here. Gold nucleus starts out at rest. The alpha particle gets closer, is repelled. You said that was what was going to happen. And the gold nucleus sort of majestically recoils in the other direction. Its speed is slower because its mass is bigger, right? So big momentum, but slow speed. It didn't. It was moving. It's just that the trail was inside the particle at first because it hadn't moved far enough for you to see the trail coming out. So it started moving. It's just that it wasn't obvious for a moment that it was moving. Now this is one possible path, but if we move the alpha particle, notice the alpha particle came in on top, and then so if we moved it closer, it'd probably look a little different, right? So let's move it a little closer. Let's say it starts out a little bit closer. Different angle, right? So in these scattering experiments, the way we talk, so the question is, how do you talk about how close to the gold nucleus was the alpha particle? And we usually talk about this vertical distance here between the center of the alpha particle, the center of the gold nucleus. This is called the impact parameter. So if it was a head-on collision, what would the value of the impact parameter be? 0. And so there's just a distance. From the center, it's the perpendicular distance from the center of the alpha particle to the center of the nucleus. Okay? And the closer we started out, bigger the interaction because it gets closer, right? So that's called the impact parameter, and it's usually called B. And so what Rutherford did, since he couldn't, of course, take one gold nucleus and shoot alpha particles at controlled distances, what he was actually doing is kind of something like this. He had some source that would produce alpha particles, not that one. So he had a source that spewed out alpha particles, and if he could have looked at what happened near one gold nucleus, and remember, this makes sense because the gold nuclei are so far apart that any given alpha particle is only going to interact with one gold nucleus. So what he would do is shoot lots and lots and lots of particles at it. So here's our source, and here's our one gold nucleus. And what would happen would be something like this. So the impact parameters are kind of random here. And we're saying that what we've got is a spherical detector. So we put this spherical detector all around the gold nucleus, and we're looking to see where the alpha particles hit, which is actually pretty much what he was doing. And except that in this program, what we're doing is we're color coding the trajectories after the fact. So a particle whose path didn't deviate by a very big angle made a cyan trail, and a slightly bigger angle was blue. And the ones that were deflected through angles greater than 90 degrees, they actually came back or coded red. And you can see that these are infrequent. So in this program, actually, we just shot 1,000 alpha particles at this gold nucleus, and you can see that most of them ended up not deflecting much, but a few really bounced back. So actually, Rutherford didn't make the measurements himself. He had a graduate student. and so he assigned the graduate student to take this little piece of fluorescent stuff that would emit light if energetic alpha particles hit it. And in a darkened lab, put it there and see what happens. Put it there, put it there, put it there. And he didn't. What Rutherford expected was actually not this, though, because everybody up until that point thought that instead of having a little massive, highly massive nucleus and then a cloud of negative stuff around them, they thought that an atom sort of had a smear of negative stuff and then maybe little tiny positive things sort of embedded in it. You've heard of the plum pudding model. And so what he expected to see, actually, was something like this. If these alpha particles hit a very low mass gold nucleus, the nucleus would be affected more strongly, but none of the alpha particles would actually be deflected very much. So basically, he wasn't giving this graduate student whose name was Marsden, a very interesting experiment to do, because he wanted him to sit in front with its detector and count the flashes and then just move it around just to make sure that there weren't any anywhere else. And so when they all saw the results, they were amazed, because that didn't agree with what they expected at all. And Rutherford was quick enough that he looked at the scattering distribution, a distribution that he was looking at a graph, but basically what he was looking at is this kind of pattern. And he said, oh my goodness, the only way that could happen is if this nucleus is really, really massive, because there's no way one of these alpha particles could bounce back unless the nucleus really was massive. You may have seen his quote where he says, it's he was as surprised as if he'd fired a cannonball at a piece of tissue paper and it bounced back and hit him in the nose. So scattering experiments like this are actually are done to probe this inner structure of various things. This was one of the first, but people do things like this all the time. Notice that we can model them using our same old, calculate the electric force, calculate the new momentum, calculate the new position. Now the electric force has changed, so do it again. So we can actually make a fair amount of headway in modeling this in ways that they didn't have open to them, because doing it by hand would not have been a pleasant thing. But you're actually equipped to do this, and you may end up doing it in lab. We'll see.